Hey, today I'm going to be presenting a computational study on how electrode surface area affects supercapacitor performance, specifically in graphene-inspired energy systems. The motivation behind this project comes from a growing demand for efficient energy storage in electric vehicles and renewable energy systems. While batteries store large amounts of energy, they tend to charge slowly and degrade over time. Supercapacitors offer an alternative because they can charge and discharge much faster, but usually store less energy. This leads to the key idea of my project: improving supercapacitor performance by increasing electrode surface area. Materials like graphene are especially interesting because they have extremely high surface area and extremely good electrical conductivity. My research question is, how does increasing electrode surface area affect capacitance, charging time, and energy storage in a modeled supercapacitor system? To investigate this, I used a simplified computational model based on a resistor capacitor, or RC circuit. In this model, the capacitor represents the energy storage system, and the resistor represents the internal resistance in the device. I implemented this sim in Python and varied capacitance values to represent the increasing surface area. The theoretical basis for this model comes from a few key equations. First, capacitance increases with surface area, shown by the relationship C is equal to epsilon A over D. Second, the energy stored in the supercapacitor is given by 1/2 CV squared. And finally, the charging behavior follows an exponential curve governed by the time constant tau is equal to RC. In my simulation, I tested capacitance values from 1 farad up to 20 farads, first keeping resistance constant. Then I ran a second version where resistance decreases as capacitance increases, to better reflect graphene's high conductivity. These results show a clear trend. In the fixed resistance model, increasing capacitance leads to higher energy storage, but also significantly longer charging times. For example, increasing capacitance from 1 to 20 farads increases stored energy by 20 times, but also increases charging time from about 30 seconds to nearly 600. However, in the graphene-inspired model, where resistance decreases, charging time is dramatically reduced. At high capacitance, charging time drops by up to 80% compared to the fixed resistance case, while energy storage remains the same. These results highlight a key trade-off in energy storage design. Increasing surface area improves energy capacity, but without improving conductivity. It slows charging. Graphene helps resolve this trade-off by increasing surface area, but also reducing resistance. In conclusion, this model suggests that graphene-based supercapacitors could significantly improve both energy storage and charging performance. While the simulation simplifies many real-world effects like ion diffusion and material structure, it still captures the core electrical relationships and provides useful insights into how these systems behave. Thank you for listening.